er ook even een microfoon bij. We hadden die bedacht voor de close-up. Mooi. Omdat we dan hier staan en dan kan die persoon ook hier kijken. En dan kijkt hij eigenlijk het meest in de camera.
Racing has always been the platform for technical innovation. Competition drives innovation. The racetrack has always been the place where new technologies are taken to their absolute limits. And as the mobile sector is becoming more and more electric, it is important that racing also becomes more electric. We need to preserve racing's ability to be at the forefront of technology. At Electric Superbike Twente, we preserve racing for future generations. We do that by building superbikes, capable of so much speed. These high-performance electric motorcycles are built entirely by a group of students. And this year, it is time to finally show what our 5th superbike is capable of. This year, it is time to race. My name is Lindy Snoek, and I'm the team manager of Electric Superbike Twente. Today, we will tell you about our road to racing. We will begin with a small step into the past, looking at the beginning of Electric Superbike. Then we will look at the beginning of our newest motorcycle. And then we will go into the present, telling you about our newest innovations and the techniques we are working on right now. Finally, we will finish with a step into the future. What are our plans for the upcoming year? So, let's start with our legacy. Electric Superbike Twente was founded in 2017 by a group of students that wanted to prove that electric motor racing could be safe, important, and also very exciting. So they started developing the first superbike. Our first 3 bikes each had their own focus point. The first one was made for reliability, the second one for agility, and the third one for power. And finally, all of these pillars culminated into our 4th superbike, with which we won our main race in Finland in 2022. And before we knew it, it was September 2022. Time to develop our 5th bike. With our first 4 bikes, we figured that we had proved our initial goal. So we wanted to do something more. We didn't only want to build an excellent motorcycle, we wanted to reshape electric motor racing, invent a technique that the entire electric motor sector could benefit from. So, how does one do that? That is a pretty big goal. It's no surprise that range is one of the biggest challenges in electric driving. You can make a bigger battery pack, but then you'll also be heavier and more slow. So, we came up with a new technique. We are going to build a high-performance motorcycle with a modular battery, so we can swap our batteries during the race. We came up with Vector ST. In that first year, we tackled some big projects. We made a frame in which the battery could be taken in and out very easily. We built a first battery pack and made a data system that could transport data throughout the entire bike. And after a year of hard work, it was September 2022. Time for the new team to take over and finish the bike. Well, it wasn't exactly as easy as finishing the bike. There was still a lot of stuff that needed to work before we're ready to go on the tarmac. So, today we will tell you about all our new innovations and the big projects we are working on, in order to send Vector ST soaring across the track. We will start with Eric, who is going to tell you about the ST of our Vector ST. Thank you.
Thank you, Lundy. Hello everyone, my name is Erik and I am part of this year's chassis engineering team of Electric Superbike Twente. Lundy just introduced to you the newest addition to our legacy, the Vector ST. And it's the ST that I'm really excited about, standing for swapping technology. This year, we took a turn into a new direction. We've opted for a superbike design that is even lighter and even more powerful. It can deliver up to 210 horsepower, which is quite impressive. However, using this much power to send our superbike soaring across the track, it does take its toll, and as Lundy said, it does so on our range. This year, we try to mitigate this effect by incorporating our swapping technology. We want to perform a mid-race pit stop where we will be changing out our old battery and replacing it by a new and fully charged one. This must be performed quickly to stay competitive against other superbikes that are heavier but don't have to stop. Last year, we already started this developing. where we completely reshaped the way a motorcycle frame looks like. With our new and modular battery pack, we can now access our battery pack and replace it within seconds of our bike. Here you can see how we can take it out of the superbike. However, this is not the end of the story. The battery pack still weighs around 60 kilograms and we cannot just lift it out. We need something to take it out for us. And for that, we have developed a new concept, a new apparatus that can help us with that. I would like to tell you something more, how what we came up with, and also how we did it, because I think it really nicely reflects how we here at Electric Superbike Twente face these challenges. So, our swap car. We started with some different concepts. Think about how can we solve this problem. Something that we do at the start of this concept phase is that we actually reach out to one of our many experienced partners. For example, in this project, we asked a company that's also just around the corner, Demcon, and with their expertise of their engineers, they guided us to the first step of this concept phase, where we came up with many different designs to face this challenge. We came up with an idea of using some sort of card mechanism that could then latch on to our battery, and using a lever system, we will then lift up the battery out of our bike. After which then a second card would be used to place our new battery. So, yeah, nice idea. But how would this take form? Now, that's in the next step, where we start making our 3D design. Here we think of every single part, every bolt, nut that goes onto our system, such that we really know how to assemble it, that there are no problems with our design, and that we actually know what we want. And that is the design you've been looking at here now. You can see we've used these swivel wheels at the bottom such that we can easily move our cart around. On the top, we have this triangular frame with these pins attached to it that would latch on to our battery, and it's all actuated by a long lever that gives us the advantage to lift the weight of the battery. Now it's time to take this design from this virtual world and bring it into reality. For this, we need parts. Now, how do we get that? Luckily, also a partner of us could help us in this project, that was Taylor Steel. Then here, also they got the opportunity to show what they are capable of by providing us the steel necessary to produce this part. Lastly, with all these parts assembled, we have now our first prototype. You think we're done? No, because there will always be some problems. We need to see if this actually works how we thought of it. So we must test it, evaluate it, see if it does as desired. And if not, it's time for a redesign, where we go through the cycle again and again until we have something that operates perfectly and which we can use on the track. And hopefully, at the end, it would look something like this, where we have our superbike standing into the pit lane. Me and my teammates will be rushing at it with our swap car. Here again, you can see how we would latch on to the battery, after which we quickly remove it from our superbike. Then the next team will do this process in reverse to replace a battery and send our Vector ST soaring over the track once more. Now I think it's really nice to also tell you something more, how our battery can deliver this power to our electromotor. And for that, I would like to give the word to Sjoerd.
Thank you, Erik, and hello everyone. My name is Sjoerd, and I'm the Chief Powertrain of Electric Superbike Twente. Having a battery swap mechanism in Vector ST allows us for a unique opportunity that has never been done within Electric Superbike Twente before. We can build two distinct battery packs. Now I hear you thinking, why would we want to have two distinct battery packs instead of just one that's the same design? The reason for this is because we're a student team and we want to learn as much as possible. When designing a battery pack, there are a lot of parameters that highly influence the performance, the distance, range of the battery pack. Since we have the opportunity to create 2 distinct battery packs, we can, for example, build one battery pack that's made for endurance, which has a higher capacity and a higher weight, so we can do longer ranges, and one battery pack for drag races. So we have a smaller battery pack that is lighter with a higher power output. For these reasons, we built 2 distinct battery packs. And although they are quite different, they also share some similarities. They are both made to have a reduction in weight to sustain the battery swap mechanism. They will both fit within the same battery pack, which you can see here. They will have the same connectors and same data communication. And they also operate on our new battery management system, which we will tell you about soon more about. Here you can see the key features of the 2 battery packs. The first battery pack is made to have a low internal resistance. To achieve this low internal resistance, you need to have a lot of cells, and to connect all these cells, we made a distinct interconnection system. The second battery pack is built and designed on easy assembly and disassembly and higher capacity. For this, we can race, with this battery pack, we can race longer. The main difference of the 2 battery packs is inside the module. Here you can see the module of our first battery pack. This module will fit 128 cells within the module. For all these cells to fit and to be connected properly, we designed our own unique interconnection system. This system is built to be very lightweight and space efficient, and with this interconnection we can connect all the cells within the module. Here you can see the design of the second module, of the second battery pack. This battery pack is designed on having easier assembly, so we can assemble and disassemble the pack quickly, and on having a higher capacity, since we can have bigger cells. On the second picture, you can see the interconnection system itself. We can easily connect and disconnect all the battery cell steps from the top, so we can gather all the data and have a good connection. What I personally really like about this design is that you can actually see the flow of energy going through the interconnection system. Once the 2 battery packs are built, we'll take it to the racetrack and we'll gather much data. This will provide future generations of Electric Superbike Twente with more knowledge on battery pack design and impact of different parameters. All this data will be collected by our new battery management system. For this, I would like to invite Mickey on stage.
Hello everyone, I'm Mickey, I'm part of the powertrain team. Now that we told you all about our battery packs, let me tell you more about how we're planning to manage these. So firstly, this year we wanted to build a BMS system, a battery management system that is safe, robust, but more importantly, reusable. We have 2 battery packs with 2 different distinct features, different number of cells, different numbers of cells inside the module. So our BMS system needs to be able to handle both battery packs. The idea of that is to make a BMS system that is used for us, future ESTs, so they can even test more batteries, gather more data, and make EST bikes more stronger. First, we started with using with the chips. For the BMS, we needed new, highly powerful chips. For that, we found NXP, our new partner. NXP is taking a great leap in the automotive-grade chips. They have custom-made chips that can be custom-tailored to fit our requirements and goals, and of course our bike, Vector ST. The major changes we're taking in the BMS allow us also to tackle other problems on the way. So for example, the change in the BMS allowed us to fix our space limitations and our wiring problems. With the new BMS, we're integrating a lot of boards together to decrease the length of the fat wire cables inside our battery pack. Furthermore, let me tell you more about our battery packs. We have the high voltage control board. This is the brain of our system. It's responsible for taking the measurements from all of the other boards and instructing them on what to do. It's also our way of communication with the systems outside of the battery pack. So for example, using the CAN buses, the main communication system on our bike, we can tell other systems on the bike what to do. Moving on, we have our high voltage relay board. This is the power routing board. The idea of this board is to have all of the power routing done through it. So the high voltage relay board is connected to the motor inverter and to the battery pack, meaning that if the high voltage control board deem it safe, the high voltage relay board will send all of the power to the motor inverter so the motor can go running on the track. But if it's not safe, it will discharge all of the power through a discharging circuit that is integrated on the same board, using a massive resistor that can dissipate all of the power inside of our inverter in less than 1 second. After that, we have our cell protection board. This is the cell monitoring unit. This is the board responsible for protecting the cells within each module. This board needed to be reusable. It needs to fit different numbers of cells. So for that, we're using every pin possible on the new NXP chip. We have 18 voltage sensors and 8 temperature sensors to make the system reusable for a minimum of 4 cells per module and a maximum of 18 cells. The CMU is also responsible for the balancing of the cells inside the module. To ensure that we get the maximum power and that the battery is fully charged, the cell monitoring unit is equipped with active balancing. We chose active balancing rather than passive balancing to further align with our goals of more space-friendly equipment and more cost-efficient. And now we get to our newest board, the intermediate PCB. The intermediate PCB is a completely new board that we made to lift the pressure of the high voltage control board. What do I mean by lifting the pressure of the high voltage control board? Originally, the high voltage control board was connected to all of the systems on the bike. So as you can see, there was no intermediate PCB. The high voltage control board was connected to inside the battery pack, all of the high voltage system, and outside of the battery pack through the CAN bus. This creates different potential differences and floating grounds that can damage our board and make it prone to higher damage or error. To solve that, we made the intermediate PCB. The intermediate PCB is the center of our new BMS. It lifts all of the pressure, takes care of the galvanic isolation on the board. This is to ensure that there is no stray current going from the high voltage relay board towards the high voltage control board, which ensures safety. Then, of course, we're not making a whole new board just to make one thing. The intermediate PCB will be adding some more features that our BMS was missing. So for example, it will have a high voltage interlock system. The high voltage interlock system will be there as it's essential to ensure that the battery pack cannot be disassembled unless it's safe. This is essential as the batteries will be operated with the operators on the swap card as seen before. One extra feature that is on this board is an extra emergency stop button. This is an extra full safe protection, so in the case of emergency, we can turn off all of the power of the bike and it can be deemed safe to touch. Now that I told you all of the steps to make our BMS safe and robust and future-proof, let me tell you about a different system in our Vector ST. So for the first time on an EST bike, Electric Superbike Twente, we have a telemetry system. What is a telemetry system? A telemetry system is a communication system that is mounted on the bike. It gathers all of the data from our data center, and then it can transfer it wirelessly to an external PC to allow us to monitor the bike from the pit stop. This is essential so we can tell the driver on the status of the bike, and we can instruct him on what to do. How does the telemetry do that? First, we have our data center. We have a data center on the bike that collects data from over 200 sensors on the bike and store it there. The telemetry is connected to this data center, and using a KPN 2G SIM card, we can transfer all of this data with a transfer speed of 1 megabit per second to our external PC. One more thing that our telemetry has is we have an offline storage. This is in the case that the connection is lost or disturbed. We can keep gathering the data for up to 300 seconds to ensure that we can troubleshoot our problems and fix our problems easier in the future. With all of that being said, let me keep this short and show you a little demo on how the telemetry will work. This is a part of the screen that we'll see on the external PC. For the demo, we decided that we'll show you 4 of our most important sensors. So for example, the throttle, the speed, battery temperature, and the motor temperature. In addition to these sensors will be a lot. So for example, for the chassis engineers, they will have the suspension sensors, the battery, like the braking pad sensors, to know the sensors of our, the temperature of our pads, and many more, up to 200. We're planning to have 25 important ones, so that the ones that we can act upon. But to show you how it will work, we have a little demo. You see as the throttle increase, the speed is increasing, how the battery temperature and the motor temperature is reacting in real life. With all of that being said, let me get off your ear and tell you more about our bodywork. For that, I will let Renke take the stage.
Thank you, Mickey. My name is Rinke and I'm Chief Chassis. This is the first time Electric Superbike is designing a custom carbon fiber bodywork. This had several reasons to do so. First, the bodywork is the shell around the internal components, which has as main purpose to protect them. The reasons to design this is first, the battery swap. This can go in a clean and efficient manner by rearranging the sections such as we want to have no restrictions whatsoever. Second reason is that the frame from last year has been redesigned to fully integrate battery pack. And by rearranging the sections, the bodywork will shape around the frame seamlessly because this frame has become unique to our bike. And the third reason for doing so is because of cooling. The motorcycles have limited space inside, and if you want to race crazy fast, you have to have an even bigger challenge to optimize our cooling capacity to the limit. Because of that, we optimize the airflow through the radiators to get the optimal cooling capacity. Additional benefits for that are aerodynamical improvements and a sleek design, which is mostly inspired on Moto2 motorcycles. So a bit more about that design itself. So we have the nose fairing, the left fairing, the lower fairing, and the right fairing, consisting of 2 parts. The parts all have flanges that bend inwards to create a seamlessly overlap and have a smooth transition between parts. We go through them one by one. So, the nose fairing. This one has a steering angle of 15 degrees possible to the left and the right, and to make the driver able to steer it. This also has an inlet, which is 1/3 of the area of the radiator behind the nose, which is the minimum inlet area for laminar flow. The left fairing has a gap spared for the high voltage cables, the CAN cables, and the manual service disconnect to be able to access them all times and to have a quick swap. Also, a quick swap is visible at this location by the holes that are there for the screws to unscrew the battery pack housing. The lower fairing has gaps for the outlets of the radiator below, which is the radiator that cools the electromotor. And the right fairing consists of 2 parts. The smaller part is fixed to the frame, and the bigger part is fixed to the battery, also to be able to swap quickly. And these gaps are also as an attachment point for the swapping card, as already seen at Eric's demo. So how do we even make this? We design and produce our own composites, but we are doing this by making molds. Each bodywork piece needs a mold. And right now, our CNCer is making these molds, and soon we will start laminating them. So we learned how to make split molds. This mold can split to the left and right to be able to loosen the product after it is cured. And also in here we can see that inserts have been made. These parts are also placed into the mold to make complex parts possible, to make these flanges that can bend backwards still are able to make and to loosen from the product. And then how do we lay these molds up? Because you can imagine you still have mold, but it's a quite complex process to lay these molds in. And we successfully made the designs. So soon we will use the carbon fiber. These are just loosened fabrics, quite flexible. And we will push them to the corners to very detailed copy the behavior of the mold. We put them in different directions to strengthen them in all the directions that are needed. And then make sure there's also a symmetry in Z direction, as you can see on the right. This to make sure also the stress in the depth direction is made sure. And then after this is put in a vacuum and in an autoclave and on high temperatures for a few hours, the product has been cured. And then it has become a very tough product, as you can see as a demo in here. And afterwards, we will only have to post-process it to make outlets, for example, for the cooling, which Sander will tell you more about.
Hello everyone, I'm Sander. I'm one of the chassis engineers of this year. I will tell you more about the cooling. Vector has really much power, 160 kilowatts and still being very efficient. But even the slightest losses result in a huge amount of heat. This is why our bike still has two components which require cooling. This being the inverter and the electromotor itself. But first, let me talk about what a cooling cycle actually exists of. We use as a liquid water, and a pump will push the water through the component which needs to be cooled. Here is the heat absorbed into the water from the component, and after this it will go to a radiator where the heat is rejected to the air. We have also a lot of sensors to keep the data all in track of the cooling. Here on the screen you can see the cooling loop of the electromotor. Our electromotor needs about 8 kilowatts of cooling capacity and has about 12 liters per minute of mass flow. To reach this cooling capacity, we chose this year for a custom radiator. This custom radiator does not has more cooling channels in the radiator, so the heat is more. So the water will reject its heat more easily to the air passing through the radiator. Not only has it more cooling channels, but it has also more is thicker, so you have a lot more thin area of your on your radiator. Then we have a duct design of our electromotor loop, which you already could see in the bodywork design of Rinke. You see over here 4 outlet streams. This is to guide the airflow outside of the radiator to the out of your bike. You can see 4 flows, 2 at each side of the bike. And this is because of aerodynamic purposes, because 2 smaller holes will have less drag than just 1 large hole in your bodywork. This duct will be quite complex shape and is made out of carbon fiber. And this is also because we want to reduce the weight of this component. Then we have our inverter loop, which is placed in the nose fairing, as you can see here on the bike. This cooling loop needs about 3 kilowatts of cooling capacity and has about a mass flow of 8 liters per minute. The cooling capacity is much less than the electromotor, so we want to focus on this by reducing the drag to make the cooling as optimum as possible. This was done by CFD simulations. On the screen, you can see the duct of the inverter loop, and you see a lot of colors. The red one is for the inlet flow, and it is the highest speed it will reach. And then the blue and the green colors are lower speeds. You can see that the inlet flow is quite high speed, but then it reduces at the sides of the in the duct. But what you want to keep is the laminar flow, so that the air is passing right on the radiator. If the inlet area is too small, then you create turbulent flow in your duct. You can already see at the bottom that it tends to become turbulent, but that's what we try to prevent, and that's why we are really on the limit here. But to have to make good use of your cooling, you want to have a good efficiency of your motorcycle, of your electromotor. This can be done by motor tuning, and Sjoerd will tell you more about this.
Hello again. Like mentioned, Factor ST is a real powerhouse. With all this power also comes losses transformed in heat. You want to reduce the amount of heat within the bike as much as possible. For the electromotor, this can be done by having a good motor mapping. The inverter within the electromotor decides how energy will flow towards the electromotor. The way this electrical energy flows towards the electromotor will highly determine the efficiency of the electromotor. But how do you know what energy will be most efficient for our electric motor, especially since we have a custom-made internal permanent magnet synchronous motor? Within the industry, the field-leading theory for this is field-oriented control. And I will quickly explain this to you so you guys know what we are dealing with on a day-to-day basis. Our electromotor consists of 3 phases, and you can see it in the 3 windings A, B, and C. Through these windings, electric flow will go through these wires and create a magnetic field. This magnetic field will create a torque on the permanent magnet that is attached to the rotor of the electromotor. This torque will eventually create a torque that's required to make the bike go forward super fast. The angle of this torque factor in the QD plane will highly determine the efficiency of the electromotor. But where do you find the most efficient angle of the torque factor? We do this by gathering a lot of data, and with this data deciding which point is most efficient. This data will also be gathered at one of our partners called SPIT. They have a dynamometer and an external power supply, so we can fully test our electromotor, gain a lot of parameters, and also know where the most efficient line will be. With this data, we can determine how efficient our electromotor will be and send Vector ST racing on the track as efficiently as possible. For now, we have talked enough about technical details. We can keep talking, but it's also important to look at the future. For this, I would like to invite Alex on stage.
Thank you, Sjoerd. My name is Alex, and I'm the technical manager this year. As you've just heard, we have been and still are working on many exciting projects. But coming back to our road to racing, what steps are left to get Vector ST, as you see right here, on the racetrack? Well, next to performance, safety is our top priority. And how do you ensure the safety of a high-performance prototype vehicle? Through rigorous and extensive testing. Luckily, we've already started with this. In our warehouse or workplace, we have an in-house dynamometer, which is an eddy current type, or dyno for short. On this dyno, we can test all the electric systems and some mechanical systems of our bike. For example, we can make sure that we can see all the sensor data, we can know what kind of temperatures are playing, we can check if the inverter is sending a smooth signal to our electromotor so we don't have any oscillations, and we can get some insights into lubrication, battery pack performance, and also some cooling. And as Sjoerd just mentioned, we'll also be going to Spit in the coming 2 weeks to do our motor parameterization and also motor mapping. One drawback about the dyno in our workshop and the one at Spit is that it doesn't actually test our bike as a complete system. That's because you'd connect the electromotor with a chain directly to the dyno. So you're actually missing the entire rear section of the motorbike, which is the swing arm, the rear suspension, the rear tire. So the entire linkage is actually not part of the equation. Well, before you head on the asphalt for the first time, you want to make sure that the bike works even with this added to the equation. Luckily, we have another partner who can help us with this, which is Twente Racing. They have a special dyno where we can test the bike as an entire system, so with the rear swing arm, with the rear tire, and the entire linkage. Additionally, on this dyno, we can also push Vector ST to the limits, as our dyno in our workshop can only handle up to around 500 Newton meters, but the one at Twente can really test the full performance. Well, at Twente, we can also do some weird tests which might happen on the racetrack. For example, suddenly letting off the throttle or suddenly jumping back on the throttle. This induces a large force into the bike, and we need to see how the suspension reacts to it and if the mechanical stability stays intact. Because we don't want to compromise the safety of both the superbike and our riders if we do this on the asphalt. Well, once we're happy with all the results, it's time to hit the asphalt for the first time. So Vector ST will be driving her first meters on her own power. While this is of course a really exciting step, it also introduces a lot of new variables which could compromise the safety of the bike and also the professional test drivers. And how do we tackle this problem? Well, we'll go step by step, starting from small and adding more variables to the equation with every step. So the first test on the asphalt will be just on a closed-off area. We'll go very slow to see if all the systems are operational as expected, even when she's outside. And after this, we'll be heading off to Twente Airport or Flugplatz Nordhorn-Lingen in Germany to do some straight line tests. In a straight line test, as it says in the name, we'll just be going in a straight line, and which each successful run will increase the speed and acceleration. With these tests, we'll be able to get some first feedback from our riders, see what our cooling is doing, and therefore also see how our mapping is performing. Well, once we're happy with all of this, it's time to head off to the famous TT Assen circuit in Assen, where we'll be testing Vector ST with corners, curbs, hard acceleration, hard braking, so real racing conditions. Now, what's important for us here is once again cooling, everything like that, but most importantly, the feedback from our professional drivers. Because after a few seconds, they can already tell us what we need to change in the setup of our motorcycle to make her handle better. Because next to power and safety, handling is a key aspect to winning races. Well, while all that's said and done, there's only one thing left to do, and that's to go to the races. We want to show off what 7 years of Electric Superbike Twente and 2 years of working on Vector ST is capable of producing. Once again, we have many opportunities to do so. from racing in the International Dutch Championship to racing against our main electric rivals from the United Kingdom and Finland. Next to showing off the racetrack, Vector ST also wants to prove the concept of a battery swap in the motorsport world. And as Eric already told you and Lundi in the beginning, we will do this by performing a mid-race battery swap during a race. Similar to a tire swap pit stop, which you may know from Formula 1, a battery swap introduces a new tactical element to electric racing. Choosing what kind of battery you swap and when you time your swap can have a great impact on the course of your race. We believe this innovation will contribute to a new tactical element which will make electric racing as a whole more interesting and exciting. As Electric Superbike Twente, we aim also to make sure that innovation is continued. And as Lundi mentioned in the beginning, we will be competing for innovation so that the electric vehicle industry gets the innovation it so desperately needs. With Vector ST, we are reshaping electric motor racing. And now, finally, Dirk will tell you who makes all of this possible.
Well, thank you, Alex. Without partners, no Superbike. My name is Dirk Sely, and I'm this year's communication manager. All these technical innovations which you just saw would not have been possible without the trust, help, and time our partners put into this project. In 2024, we already have 58 partners, and there are still more in the making to fulfill our mission. We would like to extend our gratitude for their trust, time, and effort they've invested into our project. Also, we want to extend a warm welcome to all of our new partners who joined our network, contributing with more components, gear, safety, advice, and innovation to preserve racing for future generations. Let's make 2024 our year to excel on and off track. Our road to racing began with the explanation of our legacy, which led us to the finish line in the past. But with our newest superbike, Vector ST, and our technical innovations, such as a battery swap system, telemetry, custom bodywork, and battery pack, we once again aim to compete against other superbikes. We are reshaping electric motor racing and try to push the technical boundaries of the automotive industry. For now, if you have any questions about our superbike, or for the students who are right here now and want to join Electric Superbike Twente for next year, I would like to invite you at the entrance of Hall B, where both our superbikes will be standing, and some of our team members to answer your questions. For the partners who are right now here, we have arranged a network drink upstairs, where we can also answer your questions and further talk about the future. For now, I want to thank you for your attention, and see you soon on track.